we meet again, fellow math students. It is your teacher, Mr. Knight here. We are going to be looking at integration when areas are below the x-axis. And as you've probably thought about before, curves aren't just restricted to the positive domain of coordinate planes. It can also dip below the x-axis, and well, we're just going to talk about that. It is not much different than what we've already been doing. So let's just look at it for a second, kind of think about it. So if I have some kind of curve, this red line right here, just some curve f of x, as you can see, this curve is dipping below the x-axis, and if we were to integrate or find the area under that curve, if you notice, my rectangle has to go down here instead of going upwards like this. As a result, if I'm trying to find the area of this rectangle, I'm going to have to multiply my width, my change in x, times my length, which is just going to be my y value. And since the y value is negative, we get a negative area out of this. So, when an integral has a negative area, it just means it's below the x-axis. And that has a couple of implications to it that we'll talk about right now. So for this first example, I want us to find the area of the region bounded by this curve, our bounds x equals 2, x equals 4, and the x-axis. So we're just going to set up our integral like we would normally do. I got my lower and upper bound. I have my function, which I've rewritten with this exponent up in the numerator. And if I go ahead and I integrate that using my reverse power rule, I end up with this function right here, which I can evaluate from 2 to 4. So now I'm going to just take this function, I'm going to plug in 4, and then I'm going to subtract same function, but when I plug in my lower bound, and let's see what answer I end up getting, should be negative. And if we go through these steps right here and we simplify, I end up getting a result of negative 5.5 units squared, which confirms our suspicions. It is indeed below the x-axis. Now, I was talking about how this could have an implication to it, and that's going to be in this next part right here. So, we are going to find, for this example, we're going to find the area between the curve and the x-axis for the function y equals x squared plus 3x. And it's going to be between x equals negative 1 and x equals 2. Now, graphically, I went ahead and I sketched this using just an xy chart. So I plugged in a couple x values. I plugged in my bounds because I figured those would be good x values to plug in. And if I plug them in my function, it spits out some y values. So I got a pretty decent idea what this function is going to do. I see that it dips below the x-axis right here. And so I have a little area here, and I have a little area here. Now, this area here is going to be negative when you get it. It's going to be. And then this guy's going to be positive. So if we went ahead and we just did an integral from negative 1 to 2, well, it's going to take off some of our total area. If we're finding area, we can't actually have, in a realistic sense, we can't actually have a negative area, technically. So, when we get our negative area here, I have to keep in mind that it's positive. And to help me not make that mistake, I need to split this up into two different areas, area A and area B. And I can represent these areas with integrals. Area A is from negative 1 to 0 for the same function. Area B is from 0 to 2 of the same function. And if I add those areas together, I end up getting my total area. Now, I only have to integrate once, really, because it's the same integral function. And so when I get this result, this is area A, it is negative. I need to just make it positive for my ending result. And I need to keep that in mind. Make positive. Or else I'm not going to get the true area between my curve and the x-axis. Right? It's going to take away unnecessary area. I do the same thing with area B, and then I add those areas together, and I get a total area of 59 over 6 units squared, and that would be my answer. And this is the quickest lesson of AS Math I think we've ever had. This is Mr. Knight signing off. Have a good one.